Hi there, my name is John Harper. I'm a member of technical staff at onsemi, covering automotive AMG, which is the IC division for onsemi. And I'm going to be talking about how zonal architectures are effectively the solution to some of the technical development problems. And I'd also like to introduce my colleague.
Yeah, so thank you, John. I'm Isaac Abulsad. I'm a product definition engineer at Würth Elektronik, and today also we will discuss from Würth Elektronik and passive components side how can we support such applications in the zonal architecture and smart switch applications. So let's get started with our presentation.
Okay. So great. Whoops, sorry, too long. So how do we get to having to need zonal controllers and things like that? Let's go back a bit, some history of how cars are developed. Well, you can see in the you can see my old red car from the 1990s. What did it have? It had very few electronic control units. I think it might have had electronic ignition in it. It certainly had a radio. I'm not sure if it had a central locking. Certainly the windows you had to wind by hand. One important point is, how was the wiring done for something like the headlamps? The headlamp was a classical, standard incandescent bulb, right? And the light switch and the control panel had a wire, went all the way to the lamp, powered the lamp directly, so all the current for the lamp went through that wire, thick wire, and it had to come all the way back. As there were very few external components, it had a low complexity wiring loom, and as you say, it had very few ECUs. So what happened over the years, right, between 1990 and this car I've shown from 2020s? People said, okay, let's have ABS systems, it's safer, let's have airbags, it's safer, let's have window winders, safer, and so on and so on and so on. After, 30 years later, you've got 100 electronic control units kind of added piece by piece over time. And, that's caused quite a lot of complexity. So the wiring loom complexity is much higher. There's obviously reductions in complexity of some of the wiring, right? You have a lighting control ECU now driving the headlight directly rather than having the wire connecting directly. Otherwise, with those 100 electronic control units, you would have that. So you have more ECUs to kind of consolidate control, which is the domain type architecture. But you have, depends on the exact car, right? Over 100 ECUs, each having their own software. And now you've got very high safety and cybersecurity requirements. We talk a lot about ASIL functionality. ASIL was brought in the 2010s, right? It didn't exist before then. It's very important for when you've got so many control units, self-driving cars and so on, to make sure that you have a good, safe solution. So with that background, what are the challenges? Number one is that wiring loom. The wiring loom in my old red car, right? That was very light, very simple. The one in the newer cars can go up to 70 kilograms or 150 pounds, depending on what units you want to look at in high-end vehicles. And that causes a lot of cost. It costs a lot to design it. It costs a lot to make a tool to make it. So there's a large capex. The manufacturing cost is also high on top of that. And you've got to put this huge wiring loom in the car, right? So that is one of the challenges you see by adding all those ECUs. Then we had classical fuse boxes. Fuse boxes have no diagnostics. You can't power cycle a failed load. I'll give you one example of a car with a rear camera, and the rear camera failed just as I was trying to charge it. It's an EV, right? I was backing up, and then the rear camera wasn't working, so I had to do the old way of looking outside, looking at the windows to park it, right? But it has a classical fuse box. It didn't say, okay, there's no message from the camera, let's just cycle the power and start again. You can't do that with a classical fuse box. Another thing is reserving power for brakes and steering. We'll talk about that in a little bit in a moment on that. Software complexity, you've got 100 ECUs and certain combinations of software configurations work, certain ones don't, right? So there's a huge configuration control. So if you change one of the softwares in the ECUs to upgrade it, you want to upgrade the other software to make sure you've got a proper, well-known configuration, which is not going to mess up the performance. So how do we deal with these three challenges? First of all, how do you reduce the wiring loom or wiring harness complexity? So what people have done, people who've made new cars, for example, Tesla's done this, for example, Xiaomi's done this. They start from scratch and they say, okay, we have a central sort of brain in the middle of the car, and then we connect the ECUs with a high-speed Ethernet connection, so 100 megabits, 1 gigabit per second. And so that's the communication piece of it. That uses fast automotive Ethernet. And each zone gets its own power connection. So instead of having to have 100 ECUs getting their own power, you get each zone has centralizes and distributes the power. We'll see a bit later. And just that methodology reduces wire length and wire weight. The other thing at the same time is 48 volts. That concept's been discussed for many years, even in the late 90s, talking about 42 volts. 48 volts is also used in cars today for very high power loads like starter generators, things like that. But 48 volts, the main distribution voltage, helps you reduce the size and the weight of the wires. You can see a 48 volt wire and a 12 volt wire is 48 volt wire is much thinner. Obviously, there's a limit. If you make the wire too thin, you can't really use it. But for the larger connectors, it makes a big difference. So that's one thing. Zonal control means you need to have new power concepts to do this, new products. Then you have the fuse box. I'm showing a picture of the fuse box in the car I'm driving today. It shows that this has about 150 fuses. Okay, there's no voltage, current monitoring, no idle mode control. I'll give you an example. I was went to the airport, had some document I needed in my glove compartment, opened my glove compartment, left it open by mistake. Then 1 week later, I came back, and okay, the battery was totally drained. I mean, that was a few years ago. I think maybe now there'll be stuff to stop it. But having that idle mode control and having some intelligence in the box to say, hey, John's had his glove compartment open for 3 hours and he hasn't moved at all. Maybe just turn it off to spare the battery, right? Then one of the really important things is for power management, is for powering brakes and steering. So if you have X-by-wire systems, it's important to make sure that you have enough energy left to do the braking and steering if there's a fault. So let's say you have a fault and you've got you've got an electric car, you've got your 2 kilowatt heater on or your climate control on, depending on how hot it is outside, right? And then you've got a failure, which needs all the power needs to go to the brakes and steering. You need to have smart power coordination to say, okay, you turn off your speaker system, we don't want that. Turn off the heating, that's not necessary. Sorry about the seat heating, that goes off as well. All the power then gets reserved for the brakes and steering. That's really important. That's a key development. And then you've got different types of faults with recovery, right? So rather than just saying, okay, it's broken, I'll just stop. You can't do that with automated driving. The other thing for automated driving is current monitoring. So with automated driving, you've got to make sure that that it's safe for the automated driving to work. So let's say the light system normally takes, I don't know, 400 milliamps. I'm picking up numbers here. And then suddenly it's only doing 200 milliamps. You know, why is there lights failing? Why is there suddenly less power? That monitoring can say, okay, you've got a problem. You've got to hand back to the driver in a controlled way. You can't just say, okay, sorry, I'm giving up. Immediately you've got to take over. We put it in a safe state, then take over. This is also really important for these smart switches. So current monitoring, current control, rather than these fuses. This brings opportunities for us in the semiconductor industry and also the protection of those switches with additional components. There. Finally, software-defined vehicle concept is the idea of having all the control software in the center is a good idea, but it's actually quite complex to implement. You can have different unshielded twisted pair connections, use it for 100 base T or 10 base T on S. You can see already you have capacitors and common mode chokes to isolate the Ethernet. There's a big market there for passive components there. And there's very different ways you can do things. There's one is to say, okay, I'm going to use my standard microcontroller software with then 3 different standardized devices, which you have Mac 5, PMD, depending on your microcontroller. And then one thing which we're looking at is putting all the software in the central compute, which means you just have something called a remote control protocol interface to do that. So there's different ways of doing that. It's running at different speeds. There's different complexities in getting there. But certainly the connection of all the nodes in car is slowly and surely moving to, there's a significant portion is moving towards Ethernet on that. If we look now at how this is implemented, we have a centralized power distribution unit. I'll just get my pointer on. Okay. We have a centralized power distribution unit. This does the performance which I was talking about of connecting the braking and the steering modules directly to the centralized power unit. So if then there's not enough power from the, let's say the main in an electric vehicle, this fails. There's always still a lead acid battery in an electric vehicle. So it will reserve that energy for the brakes and steering if there was any kind of failure. And obviously you can then provide stuff to the bits which are needed. You still need your high performance computing modules running. But you say, okay, your seat heaters and stuff like that, okay, they get turned off. You don't do that. So this is the importance of this centralized power distribution unit, plus the zonal control modules. The zonal control modules, okay. Okay, to the next slide. Okay, I've lost my control just a minute. The zonal control modules this shows the function of the zonal controller modules rather than power distribution. So for the zonal architecture, you have front, rear, body. So the front is running the ultrasonics sensors at your front. The rear is doing your trunk control, the rear lighting. And then there's a roof module, which is doing the antenna, sunroof, and something like that. That's connected again with 10 base T1S, but obviously CAN-FD Lin is still extensively used. And of course, these connections also, got very high-speed connections used here as well. There are, if you look at diving into the solutions of zonal controllers, this summarizes the type of products which use it quite extensively used. So a lot of smart FET drivers, a lot of LDOs, but I think this would be something which you could look at in the reference documents later as a backup information of what sort of products would fit in there. On top of this, for all of these inputs, you need passive components, and Isaac's going to be talking about that later on. So we just show a couple of products which we're bringing out is the smart power. We said that we want to have control of critical loads, and there's two types of smart power switches. There's the standard high side switch, and there's the e-fuse switch. So a standard switch, you have a load here, you turn it on and off, you control it. This would be something like an electric glove compartment is one example of that. This or a lighting system for the charging ports of the car, for example. Then if the glove compartment would be a good idea because you can have idle mode. So actually better for the glove compartment would be the one with idle mode. So we have a combination of idle mode, and it also has the harness protection. You need something called a special harness. You don't just need to protect the load, you also need to protect the wiring harness to make sure it doesn't get too hot. And this is done with something called I2T protection. And then there's capacitive charging modes to do that. So we have two different versions of these devices covering a wide range of products, which we mentioned on there. We mentioned already the different types of 10-base T1, different types of, we showed briefly the different options for 10-base T1S. We have something which will work with a standard microcontroller if you want to keep some microcontroller software in there already, which you have already. And then if you want to transition in the future, put all your software in the main brain of the car, you can use a remote control protocol interface. And these are different ways of implementing with microcontroller software, and this is with the RCP. So we have devices to cover both. I'll just show two of them. One is this will work with a microcontroller. Again, the details you can look at in the discussion. You see here quite nicely there's the line protection common mode chokes in there. Then you have RCP. This is has its own embedded, pre-programmed state machine or microcontroller in there to control the nodes directly. For example, lighting products. So one of the lighting products we're just bringing out and which we'll be showcasing in detail later on is the Gen 4 gate driver family. You can see you have boost inductors here, so you've got a interleave boost, and then you have multi-channel buck stages. If you look at some lighting designs have maybe 11 channels. They have a lot of buck channels, and obviously generally one boost channel to support that. And that requires a lot of, has a lot of, technical thought needs to go into the design of these inductors, because this is all kind of integrated, and then what's remaining is the inductors, and that's a challenge to make sure that they're efficient and compact and work well. And Isaac's going to talk about that. As we hand over to Isaac.
Okay, thanks, John. So yeah, it was really an interesting introduction about the transition into software-defined vehicle, but that also comes with a lot of challenges. And today we are going to talk about electromagnetic compatibility, or EMC, where we need to take care of this topic from the beginning of our design. Just a quick introduction about electromagnetic compatibility. We have two types of EMC. One is electromagnetic interference, which means which emissions are coming from my application to the outer environment, and the electromagnetic susceptibility, which means also how immune is my device or application against any external noise coming from. So depending on the qualification needed, you might need to do the EMI testing and the EMS testing. And in the EMI testing, we have the radiated emissions, and the conducted emissions. And for the immunity, we have the radiated susceptibility and conducted susceptibility. Taking a look on the EMI cycle or testing cycle, of course, we see while we are doing our design, we have the lowest cost. So it's always good while doing the PCB design that we think about EMC or EMI, and that we design in some filter components. Even if it's redundant at some point, it wouldn't be a huge problem to remove it afterwards. And when we are feeling comfortable about our design and ready to get it tested, we can go to the pre-compliance, testing the prototype, which is also offered by Würth Elektronik. You can do some debugging to check what kind of changes need to be done, if there are any. And then you go back to the first stage, do the changes, then doing the pre-compliance testing. And when everything goes well, then you can go for the full compliance testing, which is, of course, the highest cost. In our PCB or in our application, we have mainly these two type of noises that can happen in the circuitry. So we have the differential mode noise, which comes from one power line to the other one, and they are in opposite direction. And there is also the common mode noise, which comes from both power lines and coupling to the ground, and they have the same direction in this case. How these kind of noises come in the application, we can see a lot of coupling mechanisms in a very simple circuitry, where we can see here, if we have a noise source connected with the data line, with the power line, and close to it there is another component that can be affected by it. So we can see here, we see many coupling mechanisms. And so on the right side, we can have a galvanic coupling if we have a common impedance on the line of the power line. And that's one type that can happen. Another type is, of course, the inductive coupling. So if we have here a power line or a data line, and adjacent to it, there is another line carrying power where there are some switching or a lot of data is being sent. And it just acts simply as a conductor, where when a current is flowing in this inductor, they will then make some voltage change on the adjacent lines in between. Same concept can be used for capacitive coupling. If we consider these two lines as plates, and then we have the dielectricum of the PCB in between, then they act as capacitors. So we have these parasitic capacitance that can cause also some noise coupling into data lines or power lines. And also we have the radiation of the source. So it could happen that due to the electric and magnetic fields, that we can radiate some noise to our noise sink. John already showed also the block diagram of an ECU here, taking a deeper look from the passive component side. So we can see here we have a lot of DC-DC converters, or a lot of communication lines that we would need due to the high demand of communication between the ECUs, to be always monitoring if everything is going well, the currents and everything is fine. And we can see here that whether for the power conversion, we have a wide portfolio of power inductors, or also for the filtering, whether it's a common mode filtering or differential mode filtering using an LC component. And depending, of course, on the amount of attenuation needed, we can use more than LC component in our circuitry, going to the power management IC, and then whether to whatever application we need in the car. If it's the windows, if it's the trunk, if it's the brakes. So we have different loads in the end. and then we need to communicate through the microcontroller with the different communication protocols to the other ECUs or the main microcontroller. So we can see here also the COM mode chokes for communication lines that can be used, and also electromechanical components that can be used for fixation of these components. So just showing some examples of the new products that we have on the portfolio. So we have the CNSA, which is a COM mode choke in a size of 1210, 100 microhenry, used mainly for communication and interfaces. And this one is a bifiller one, so you have a very good COM mode noise attenuation, while the differential communication stays untouched, or there will be no distortion on that. This one is tested according to IEC 62228-3, which makes it fully certified to be used in automotive application. For the power conversion, since we were talking also about the 48-volt systems and the need of higher switching frequencies, so we have newly on the product portfolio the flat wire inductors. So we have introduced the flat wire inductors into the portfolio because they offer a very good behavior when talking about higher switching frequency using silicon carbide or gallium nitride applications. And these flat wire inductors, they come in different sizes, they have different core materials, and of course with different properties that fits for most of the applications that you would need in the automotive or the car development. So here one example of our flat wire inductors is the XHMA, which is the extreme high current molded inductor for automotive. It comes in 5 different sizes, and it has a hyperflux core material, which offers a very good behavior at higher frequency. And it can take currents up to 35 amps. If you would like to know how the rated current is being measured, you can take a look on our data sheet or application note ANP096, where it explains how the rated current is being measured to the IEC standard. However, you can also use our custom rated current calculator in Red Expert, where you can give your length, width, and thickness of your copper trace, and it will give you the rated current that should be expected for this component. So this inductor offers a very good EMI behavior and also fits perfectly for DC-DC applications or power conversion or even filtering. One more aspect when talking about automotive applications, that we always need to have reliable components that work perfectly over the whole lifetime or life cycle of this part. So another important aspect is the thermal aging for molded power inductors. For that, we have also an app note showing case what differences that can happen when the inductor gets thermally heated or induced by aging, that the Q factor can change drastically. So you can still measure the same inductance value, but then you will have a big fall in the Q factor and the inductor will not be usable anymore. So I recommend you to take a look also on this app note and check all the details in it. Now, going from the PCB to the grounding and the cables that are being used. So for a good grounding, we have the soldered contact finger for EMI suppression, or the CSFA. So this contact fingers can be used to have lower impedance loops to the ground or chassis. and also it can improve the EMI behavior in this case. These are gold-plated, so they are corrosion resistant. And also by applying pressure or temperature, then there will be no influence on the characteristics of these contact fingers. They are suitable for pick and place, so they can be placed with all the other components that are being assembled on the PCB. And as I said, they can be used for creating this low impedance path to the chassis in case there are some bigger loops on the PCB. On the wiring side, we have also the cable ferrites for EMI suppression. And as you can see here, this diagram shows perfectly the different frequencies that can be used. So we have materials that cover the frequency range of the components. We have at the lower frequencies the manganese zinc, or if we go a little bit higher in frequency, we have the nickel zinc and magnesium zinc. And we have the new material, the nanocrystalline material, which covers a broad range of frequencies that we have. And this comes also in different shapes and sizes. So feel free to check the website for what you need, and you will find it on there. Here is a reference design that we have, or onsemi has developed by the use of Würth Elektronik passive components for a front light controlled with a 10-base T1S. And this design is a modular design, as John already explained. There are different DC-DC converters, whether with the two-phase boost and two buck channels, or even higher amount of channels. And we have also the MagPhi. So why I say it's modular, because if you look here, we have like the different PCBs that can be interconnected together and used for different things. So we have on the left side the 10-base T1S Automotive Ethernet using the NCV7410. And for the LED driver module, we have the NCV78964 and NCV78925, which has the 2-buck and 2-boost plus 2-buck, or interleave boost plus 2-buck converters. And we have used the inductors from Würth Elektronik, like the PDA, the HAPA, LHCA, so for the buck and boost stages, but also the EMI suppression ferrite beads like the CBA, to achieve the highest efficiency while doing the power conversion and also meet the EMI requirements. So the key takeaways while designing any application, also especially for automotive, consider EMC from beginning of the design, designing your filter components, and on the other side, the PCB layout should be optimized so that you have lower loops, lower inter or cross-talking between the lines, and trying to make it as perfect as possible. I know it's a hard task, but still that's something can be worked on. Of course, for the power conversion, using the optimum power inductors, taking also care that we use for power conversion shielded power inductors, and the core material that fits for the bright switching frequency and also the current limits.
Okay, so the conclusion from our side from the system point of view, models in production today, we've talked about those. How are we going to move to models which are going to be designed 2028 and beyond? What do they need? So we're going to have zonal controllers with door zones. That's going to mean zonal control with automotive Ethernet, or also CAN connections, or in some cases link connections, but more and more Ethernet. That drives the need for Ethernet, MAC-PHYs, PHYs, RCPs, PMDs, drives the need for common mode chokes. Lights are now controlled from a front zonal controller or a special lighting connected to a certain lighting module, right? You don't have the light switch controlling the lighting ECU. You're going to get software controlled lighting where the light switch is just one part, goes to the central brain, and then that controls the lights. And those that requires advanced DC-DC converters. We have a family of lighting products to support that. That requires the inductors from Wurth to do that. Modularized 48-volt wiring looms. That's a topic for all of us. We're going to be moving from 12 volts to 48-volt systems. Some people have started early on that. So we're getting more and more interest for 48 volts. So we're going to see 48 volts coming in. Some guys are even saying everything goes 48 volts. Is that going to happen? There's a lot of challenges in doing that. Maybe yes, maybe no. We're well prepared for it. If our customers want to do that, both of us have the components to do that. Exactly. And then the software-defined vehicles and the support for automated driving is changing the way of doing things by having the, again, network connectivity, and those network connectivities are obviously driving, we're suddenly having higher bit rates on more parts of the car, not just for the cameras, but for everything. So EMI becomes much more important. We want to have solutions to address EMI, and you want to have solutions which can deal with those fast speeds without generating EMI in the first place. That means from our point of view, as a semiconductor company, we want to make sure that our edges are suitably switched so you don't get EMI. And from a passive component company, you have ways of filtering those, making sure that even without filtering, the software runs reliably, and that also needs special characteristics and modifications of our hardware to make sure that happens. So it's an interesting challenge we're seeing as cars move towards software-defined vehicles, moving towards zonal, moving towards 48 volts. So with that, I'd like to hand back.
Thank you very much, John and Isaac, for presenting today's materials. We do have some questions that are coming into our email as well as our chat. Again, if you do have any questions whatsoever, feel free to message us in the chat or email us at webinarteam@we-online.com. Our first question here looks like it might be for onsemi. It says, what products do you have for 48-volt automotive power net?
So that's a good question because we just finished off on that topic. We have the lighting products we've shown are already working for 48-volt power net. We have LDOs we're just bringing out for 70 volts and 90 volts. One of the topics in discussion in the 48-volt arena is what is the maximum voltage? Is it 70 volts? Do you have 70 volts, 40 milliseconds, which you see in VDA 450? Or do people want to have more? Do people want to have less? So that's an open discussion. We have voltage regulators which can support that too. We have Loom products in production to do that, in development to do that, and our 10-base T1S products will also support 48 volts. So moving forward, all products we do it looking at 48 volts. And I forgot to mention we have, of course, in development 48 volt smart FETs, of course.
Thank you for your explanation, John. Our next question here is, what is the voltage rating of the XHMA series?
So for the XHMA series, we have 120 volt rated voltage. So as John already mentioned, we already have the right components to support the 48-volt systems. And even if in the future it goes higher voltage, we still have the components that can be used for it.
Yeah, what you see is there's discussions on how big is the transient on 48 volts, how much is allowed. There's still open discussions on that. Some guys say, if you consider something as a double error or not. So, but it's still fluid. But again, we have to be prepared for all situations. And I think both of our companies are supporting that.
Yeah.
Absolutely. Thank you for the explanation. Few more questions have rolled in. When will the SmartFET products be released? Ooh.
So the SmartFET products are going to be released starting this quarter and be rolled out over the course of the year. So these are the 12-volt parts rolling out definitely this year. And of course, we're ready for the 48 volts too.
That is going to be a big release, and we're looking forward to it. Our next question, do you have higher current inductors for OBC DC to DC conversion?
Yes, we do. So we have also on our portfolio the HCF80, which is also flat wire high current inductors that goes up to 75 amps. And these are THD, so they are also vibration resistant. That can be used also for such application.
Short, sweet, and to the point. Thank you. Scrolling through a bit of our chat questions here. And again, if we don't get to your questions, we will be answering them after our webinar because we are running out of time. This question is, how do you perfect arc detection in 48-volt systems with your 48-volt high-side switches?
So we haven't released those projects yet, but clearly arc fault detection is something which is an important aspect of 48-volt systems. So arc detection is well known as a problem, and that should be addressed. We don't have those products released, so I can't comment further on how we're doing that.
Very good point. Thank you. Our next question, what kind of requirements are present? WRT circuit protection from Ethernet communication?
So for Ethernet communication, you have the protection is, you would have we have the common mode choke and the capacitors on, and that's the isolation, so maybe that's protection. What you also get is sometimes you need ESD protection online, so you have onsemi is a family of ESD products used for protecting Ethernet cables, CAN, LIN, or whatever. So sure, the two Zener diodes in series, basically. Supporting those for ESD protection purposes. So that's what that looks like.
I feel like there's all different requirements for all different components and all different designs. So, and then we are going to wrap things up here. It is 9:45 a.m. Central Time. Our final question, is there a POODLE or Power over Data Line Class 15 is that T1L reference design available?
We don't, onsemi doesn't support T1L, but maybe you have.
We don't have our reference design for a T1L class 15, but if you are designing this, we can definitely help with that.
All right. Thank you both, John and Isaac, for presenting today's materials. We greatly appreciate it.